today this is, what did I say? Oh yeah, it's going. All right, so this is 6th grade, from a 6th grade workbook. And the first part of it is basically just a history lesson talking about different units of measure through history. Like a W was the distance between your elbow and your middle finger in ancient or medieval times. A span was the distance between your thumb and your pinky finger stretched all the way out. A fathom is the distance between the tips of your middle fingers when a person stretched their arms all the way out. These are all like real units of measure that have just fallen by the wayside because people quit using them. Make sense? In the Yupik culture that I used to teach in back when I was young, like you guys in Alaska, we did a whole measurement unit, and the only word I can still say 30 years later is Tailuyanak, which is the distance between your breastbone and your finger. It's about a yard. Tailuyanak. Only one I can still say. But so in this type of book, that's kind of what we do. Now, I gave you this next page because it's really important as an elementary teacher. You kind of have a frame of reference, and we also give our students that frame of reference. Like my dad called me one time and said, "Hey sis, I'm working on the car. How big's a millimeter?" And dummy me says, "Well, there's 10 millimeters in a centimeter and 100 centimeters in a meter." And he's like, "No, damn it, I'm trying to find a wrench. How big's a millimeter?" I was like, "Oh, well, it's about the thickness of a dime." Because that's what my dad needed in that real life situation. And so what this second page does is it gives you some of those real life comparisons so you can use them in your classroom. Okay? So I gave you that information. Then we're going to come over here and let's look. Notice I've skipped all the way to problem 3. In the 6th grade textbook, there was a whole lot of problems between introducing those units to them and where we got here to problem 3. So they did a lot of measuring around the school. They measured body parts. They measured how far it was to the cafeteria. They measured, the height of the playground, the swing set. They measured all kinds of stuff like that. So now we're to problem 3, and we're trying to get them to now get some type of sense of how large things are. So at your elbow, with your elbow partner or at your table, could you guys answer these 4? Like the weight of a dog, what's the best estimate for a weight of a dog, including appropriate units? Because look here. Would we use fluid ounces at all to measure a dog? No. Fluid ounces is capacity, right? So hopefully at a student's table, you'll hear them say, "No, that's liquid. We don't use that for a dog." You're listening for those type of arguments.
Really small dog if it was 18 ounces.
The amount of milk and cereal was 1 cup. The height of your classroom.
You agree with that?
But how big is 1 mile?
I guess so.
Except for in math, we call that inductive reasoning. Your past experiences,
Is that what you're putting?
like just
Yeah.
living life,
That's what I want to write
about life. Like the fact that it's probably not going to be 110 outside today. Because your life, your past experiences told you that March does not get to be 110. You don't need any scientific reasoning for that other than inductive reasoning, and that's what that is. When we, in math, it is literally okay for students to use their prior knowledge, and that's what inductive reasoning is prior knowledge. So let's look. So what'd you guys decide on the weight of a dog?
15 pounds.
Okay, I'd agree with that. The height of your classroom.
90 inches.
12 feet.
Do you think that's 12 feet?
I mean, mean, that door's probably 8 feet. 8 or 6 feet.
I thought is a door 8 or
I
7?
always-
My house is 8.
I learned 8 feet for doorways too.
Okay,
Mine's
so
house
8
is
feet for doors. Alright, we'll go 12 feet. Okay, the length of your bed.
6 feet.
Okay. And the amount of milk in a cereal bowl. Okay, yeah, I agree with all those. Alright, so, now, in customary measure, the rule of thumb is, if students see customary units, inches, customary, we're talking about standard, not metric, right? The rule of thumb is they use fractions, okay? The reason we want to teach them to use fractions is because even though they may know 0.5 and they may know 0.25, do they know the decimal equivalent of these? No. So we don't want to teach them to go back and forth. Also, the metric system is designed to be used with decimals. This system is not. It takes fractions. So that's why it's just best, rule of thumb is that we teach them customary units, use fractions. Think about it, when you read a recipe, when it tells you how, if you need half a cup of sugar, does it say 0.5 cups? It says 1/2 with a fraction, right? That's why we have to teach them to use fractions with customary. So in this one, what is the precision of this ruler? What's it marked off in? 1/4. So the precision is 1/4 inch. These are marked off in fourths. So what would this be? This first one is 1/4. What's this one? 2/4, which is the same thing as what? 1/2. Then 3/4. What would the precision of the second ruler be? 1/8. Yeah, because there's 8 pieces, so it's 1/8. So if we go in, that's 1/8. 2/8 is the same thing as what? 1/4. Then we have 3/8. 4/8 is the same as 1/2. See how we can keep going? What comes after 4/8? 5/8. 6/8 is the same as 3/4. Then 7/8. Then 8/8. Oh, I forgot to put 7/8. 8/8 is the same as 1/2, right? Can't zoom in when I'm using paper. If I was on my iPad, I could have went zoomed in. So what about this one? 16ths. You almost never see anything in the school system less than 16ths. You could get something down to 30 seconds, but that's gonna be in like high school in the shop class or the automotive class where they're really looking at very fine measures, okay? All right, so rule of thumb, customary units, what do students use? Fractions, okay. So here's where we get to your dimensional analysis, the very beginning of it, okay? So when we start and we just have like one-steppers, we call those like units of conversion. Here are our basic units. I also sent you guys a QR code yesterday. Did you guys get that? That had like 4 pages of a whole bunch of different conversions on it. That's like the set you get for your test, all those different conversions, okay? But this is a table, 2 pints is the same as a quart, 4 cups is a quart. Do you guys know the little picture that we draw in elementary school to help students learn this one because they may not get these conversions like on a state test or something?
Look like a big G.
Yes, yes. So we make a big G for a gallon. So that stands for your gallon, and in each gallon, there's 4 quarts. So we draw 4 big Q's. This would be the perfect time for color with purpose, Miss Stockton. Okay, so 4 quarts. In each quart, there are what? 2 pints? So in each quart, there's 2 pints. And then in each pint, there are 2 cups. That's too close to pink. Let's use gray. of those little P's. So then, if students learn how to draw that, if they get to a state test and the state test says how many pints are in 2 quarts, they have that picture in their head. Or how many cups are in 3 quarts. They can actually make 2 conversions on that one. So they know if they have 3 quarts, they have 3 Qs, and there's 2, 4, 6, 8, 10, 12 cups in 3 Qs. Make sense? So that little mnemonic works for capacity. Customary capacity, okay? So that's one thing that we teach. Now here's another one. We use strip diagrams like we learned in number sense. So let's think about this. If we know we have 3 gallons, right? And I want to know how many quarts there are in 3 gallons, I can draw out 3 gallons, and each gallon can be a different color. Like, I think this is like yellow, orange, and red in the real book. Then each one of those gallons I know has 4 quarts, so I split each one of them into 4. So now this is essentially the same thing as the drawing that we just drew. 3 gallons is how many quarts? We can just count them up, right? 12 quarts. So let's look down here. So here we've got 5 yards, and they've drawn out 5 yards for us. How many feet are in a yard? So we need to split each one of these into 3 feet, right? So 1 foot, 1 foot, 1 foot. That's the end of that one. Oh, that one was a nice good. I didn't get that one even. You guys didn't see that. You gotta see the end. Hi, come on in.
Put my drink in here.
Yes, back there, Blue.
Yeah, thank you.
You're welcome. I figured somebody would be back for it.
Yeah.
So if each one of those divisions is 1 foot, and I drew out 5 yards, how many feet are there in that 5 yards? 15. So the other way we can do that is we can use proportions. I am also a science teacher, so I like to connect math and science at this point. And so this is how we do it with proportions. At the very beginning, we write what we have. I know that I have 5 yards, right? Then each one of these boxes or marks I make in this table has to be equivalent to 1, which is why you see this little 1 right here. Because all we're going to be doing is multiplying by special ones. So I am trying to get rid of yards and find out how many feet I have. Whatever I'm trying to move out of or convert out of, I have to get that one on the other side of the fraction, bless you, so that they will cancel. Because now I have yards in the numerator and yards in the denominator. So anything over itself will cancel. So here's the rule. Which one's bigger, a yard or a foot? Whichever one's bigger, that's your 1 whole. Then you answer how many feet are in 1 yard. 3. So there is your special 1. At this point, yards have canceled, and the only thing I have left is feet, which is what the question asked. How many feet? So you multiply straight across the top. 5 times 3 is 15. Multiply straight across the bottom. Phantom 1 times 1 is 1. Divide. 15 over 1 is 15. And what unit do we have left?
3.
That is one-step dimensional analysis. So we go from strip diagram into fractions and proportions, right? We're multiplying by special ones is all we're doing. We just have to choose the one thoughtfully so that we can cancel units we don't want, okay? So let's look at another one. Going the wrong way. So this time I have 2 pounds and ounces, right? How many, off the screen, here we go. How many ounces are in a pound, do you know? 16, good. So, we could do this 2 different ways. We could, when your students first do it, they're gonna go, okay, there's half, and then if I cut half in half, I have 4s. And if I cut those in half, I have how many? 8. And if I cut those in half, I have 16. So there's 16 ounces in that pound. And then all of a sudden, one of your students is gonna go, Miss Allie, do I really have to draw 16 of those little things? Can't I just say there's 16 over here and there's 16 over here? And you'd be like, why, yes, you could. Because we always look for shortcuts, right? So then you'd say, so how many ounces are actually in 2 pounds? We'd say, well, that makes 32 ounces. Now, at this point, we make them practice with the dimensional analysis. And they're gonna say, yeah, but I can see the answer. And the answer to that is yes, but the dimensional analysis questions when you get up into middle school and high school are gonna get big and hairy. And if you don't learn how to do them with the tiny ones, you're really not gonna be able to do the big hairy ones, right? So we're gonna start off making our very initial, how much do we have? We know we have 2 pounds, right? LBS, bless you. In this case, we have no denominator, so it's just over 1. I know that I want to get out of those pounds. I'm trying to figure out a different unit. So since I know I'm trying to get rid of those pounds, I know they have to go in the bottom so that they will cancel, right? That's the only way for me to cancel. I'm trying to figure out not pounds, but what? Ounces. So ounces needs to go in the top. Which one's bigger, pound or ounces? So that's your 1. And then you answer the question, how many ounces in 1 pound? 16. What's the only unit we have left? Ounces. So we're good there. Multiply across the top. 2 times 16 is 32. 1 times 1 is 1. Divide if you need to, but 32 over 1 is just 32 ounces. Makes sense? Okay, now, let's go down here to this bottom one. Can we do that? Alright, because I'm going to show you what one looks like when maybe you don't go straight to, well, this is quartz. Let's do, can we do how many, yeah, let's just do it the way it is. I'll wait and do the bigger ones later. So, what do we have? We have 16 quarts, right? And what are we trying to figure out? Trying to figure out gallons. So I know quarts has to go on bottom, gallons on top. Why did I put quarts on the bottom and gallons on top? Gotta cancel those out. So you gotta have 1 on top, 1 on bottom. Now, at that point, notice there's no numbers in there, right? Because at this point, I'm just picking units. So now ask yourself, which one's bigger, a gallon or a quart? So there's your 1. How many quarts are in a gallon? 4. Remember we drew 4 cubes? So the only unit we have left is gallon. We multiply across the top. 16 times 1 is 16. Invisible 1 or phantom 1 times 4 is 4. Here's one where we actually do have to divide here on this last step. 16 divided by 4 is 4. So 4 gallons. So if we were doing it with the strip diagram, I know that there's 4 quarts in a gallon. So 1, 2, 3, 4. Mark it off. 1, 2, 3, 4. 1, 2, 3, 4. So I have 1, 2, 3, 4 gallons. So we can show it in 2 different ways. When I taught middle school and high school, to get an A in my class, you had to show me how to do something 2 different ways. Like if you do one way, that's a B. But you have to do 2 different ways. Make sense? Okay. practice problems in here that you can kind of see how you would go through in a 6th grade classroom and help connect it to real life, right? If you know a giraffe is 18 feet tall, how many inches is that? So we could take after, right? So I know I have 18 feet. So I gotta get rid of feet, it has to go down here. What am I trying to go to? Inches. So inches in the top. Ask myself which one's bigger, feet or inches? So that's your 1. How many inches in a foot? 12. Multiply across the top. Woo, 18 times 12. Let's see. What if I do 10 and 8? Let's just do this. 10, oh, thank you. 216? Yeah. Over 1. All right. Customary units of measure. So we learned a few things about teaching, right? You have to use fractions in this system. Make them use fractions in this system and explain to them why. In real life, when you're in this system, people don't use decimals. They're not out there, okay? It's not divided up where we can use decimals. If we want to use decimals, we have to go to the metric system, which is what we have next. Notice I give you guys some like debrief questions so you can kind of see the things that you would ask your students in the end to make sure they have that conceptual understanding, right? We're not just making them convert 30 problems and say, okay, they got it. We're asking really thoughtful questions like, explain to me how you do it, right? Explain to me what happens when this happens. Like if you go from smaller units to larger units, from inches to feet, does the number get smaller or bigger? It's smaller, right? When you go to bigger units, the number gets smaller. When you go to smaller units, the actual number gets bigger because it takes more of them, right? Okay. So you have to ask those comprehending questions before you can truly assess your students' understanding. With me? All right. Now, how does that differ from metric? Let's look at metric real quick. How do we approach that differently in the classroom? Well, first off, we talk about here at the front that the metric system, the whole purpose of its I don't want to say discovery, because nobody actually discovered it, they created it, right? We created these measurement systems to use, just like our enumeration system. The metric system was created in France, okay? And it is designed to match exactly with our decimals. And so kilo means 1,000 and milli means 1,000. It's always powers of 10. If you flip it over, we have a relationship again that gives you, where's my millimeter? Right here, millimeters. Oh, they have the thickness of a CD. Do you guys even see CDs anymore? This book's like from 2011, right? Thickness of a dime is what I always use, right? How big a dime is? All right, so again, this is just for your teacher reference, okay? So you know real life objects that are about that size. Now, this is the fun stuff. Have you guys ever used a place value chart to convert your metric systems? Like I know that they teach you to move the decimals, but have you ever actually seen it in the chart? That's awesome. It's pretty new. So if we come over and look at one, let's look here at A. So here I have 3 centimeters. That's my given. Can I zoom in? I have 3 centimeters, so I place the 3 in the centimeter hole. Its decimal is right there, because it goes at the end, right? 3. I need to move the decimal to where it's at the meter name. So if I move the decimal over here to the meter name, so it comes over here now, what has to go right there? I need a 0 placeholder, so that's why it's 0.03. So right here, if it's 4 meters, the decimal is here at 4. Where am I going to move that decimal to? millimeters. So move the decimal to millimeters, and what's gonna go in all those holes? So 4 meters is how many millimeters? 400, good. And this chart lays directly over what that we learned in number sense. I heard it really quiet. Yeah, I heard it over there. The place value chart, right? So this is, see, here's our ones place, our that's actually wrong. It's right on the page in front. That's the tenths place, the hundredths, the thousandths. All right, so let's do 55 millimeters. Decimal is here. Where am I taking it to? So if I take it to here, do we have to put zeros anywhere? No. Now it just becomes 5.5. Where's the decimal right now in 1,004 meters? The end of the 4, right? Now, what do I need to take the decimal to? Kilometers. So I'm gonna move it over here to kilometers. So it goes on that line. So 1.004. We good with that? So, in the customary, because we use fractions, we use the strip diagram for our second way of doing it, other than dimensional analysis. But because the metric system is designed to go with the decimals, we use a place value chart as our second way of doing it. The way that works for both of them is the dimensional analysis, where we're using our fractions and proportions.
Would you do, the second one?
Which
like
one?
the 4
What?
meters to millimeters?
4
'Cause I
meters
didn't
to
do that.
millimeters, so if I
Yeah.
move this one down here, should be 1, 2, 3, so 4.
Oh, okay, okay.
We good with that?
Yes,
We go ahead and do
thank
this
you.
one, so 45.3 meters, right? So meters, because it says meters, that is where the decimal goes, okay? Now, I'm moving it to what? So I'll move it down here at the end of millimeters, put those two on, so now it's 45300. We okay with that? All right, now, which way works every time? Let's do this one. Can we flip over here and do 6? Oh, no, that's how many meters? Let's do this one, 7. All right, so we're gonna use dimensional analysis. I know that the Empire State Building is 0.380 kilometers tall. And I am trying to figure out how many meters that is, right? So, I know that KM goes in the bottom because I wanna what? Gotta cancel it. But I'm trying to figure out what? Do I know how many meters are in a kilometer? I do, right? Which one's bigger, the kilometer or the meter? The kilometer. What does the prefix kilo mean? 1,000. So there's 1,000 meters in that kilometer. So if I cancel there, multiply across the top, 0.380 times 1,000 is what? 380. Phantom 1 times 1 is just 1 in the denominator, meters. So dimensional analysis works the same in both systems, but our second one, the way that we teach them in elementary school to get them going, is different. Strip diagrams for the fractions, place value chart for the decimals and the metric. When they get to upper middle school, we move them into dimensional analysis on through high school. And how many of you guys have been doing dimensional analysis in your chem and your physics classes? Probably here at the university. Okay, so that's our next one here is our practice. Okay. So we're gonna now
I one time did, but I couldn't get past anatomy. I was like, I can't get past anatomy, I'm not gonna be able to get through physiology either, so my husband was I would have been like, it's that. But, yeah.
Miss Stockton?
Yeah, but-
You only gave us 2. We did one.
It's failing once you get the program. Thank you.
2, 3. 1.
Yeah, for real.
Like, I'm fixing applying the
I'm
program.
fixing to get the program.
I know.
All right, so this is, I think it might be on Google Classroom, but I printed you guys a copy
I can't
anyway.
take any more until I get the
All right, so let's look at the directions. This is a multi-step practice, so this is more along the lines of what you would see in high school and here at college. Because we're gonna be using like powers, right, squares and cubes, and how do we take care of those in dimensional analysis. And we're also gonna be using some that have numerators and denominators, such as miles per minute, and have to change, like say, miles per minute into feet per second. So how do we do that in the top and the bottom? So let's look. When we're done today, at minimum, to be complete, you need 5 problems off the first page, because those are the easiest problems. You need to pick 5 problems from page 2. Remember how we do spicy, medium, and hot? Or so what would that be? Mild, medium, and spicy? So mild on the front page, medium on the second page, and then on the spicy page, on page 3, you only need 2 problems. Okay? You do not have to do the whole thing. So, let's do 1 problem on the front page together to get us going. Okay? Which one you want to do? 5? How many decades are equal to 1.7 times 10 to the 25 minutes? Okay. So we got 2 things going on here. We're going from decades to minutes, so that is our unit conversion. But we also have scientific notation, so you're gonna have to think back to chapter 7 of Number Sense 2, where we did our decimal stuff, right? So, do you guys mind if I switch to my pencil? Can you see it if I switch to my pencil? Let's see, so we're gonna do it science way, and I'm gonna start with how many decades are equal to this? So this is what I have, 1.7 times 10 to the 25th, what, minutes? So first thing I'm gonna do is go minutes to hours. Is that okay with you? Then hours to days. Then days, am I off there? Then days to weeks. Weeks to years. And then finally, I can go years to decades. So your first step is to make your path of how you're going to get from what you have, minutes, to what you need, decades. And as you go along your path, look here. Minutes have to cancel, so it goes to the bottom. My new unit is hours. Hours has to cancel, so it goes to the bottom of the next one. Now I'm in days. Notice that there is a top and a bottom, top and a bottom, top and a bottom, all the way across, so I can keep those ones balanced. You with me? All right, so let's go in and fill in our special ones. I'm gonna go in and put my ones on the bigger unit. So an hour is bigger than a minute, a day is bigger than an hour, a week is bigger than a day, year bigger than a week, decade bigger than a year. So my ones go all the way across the top. Now, I answer the bottom. How many minutes in an hour? 60. How many hours in a day? How many days in a week? How many weeks in a year? How many years in a decade? 10. So once you finish canceling, what's your only unit left? Decade. Multiply across the top, multiply across the bottom. Last step is divide.
So we multiply 1.7 times 10 to the 25th.
So if you multiply that all the way across the top, you get 1.7 times 1 times 1 times 1 times 1 is 1.7 times 10 to the 25th. all over. Now what do we get down here? 60 times 24 times 7 times 52 times 10. Oh my goodness, I got the calculator, it doesn't work. Square line.
5,241,000.
Whoa, 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 whoa,
I'm sorry.
5 million, just call it out in digits.
Oh,
241,
600.
600. All right, now divide. Do you know how to put it in? To your calculator? Do you want me to get the big calculators? Do you need them? I'll go get them. You gotta know how to use those for the test, right?
He's going to too. I'm sure that was the one that was supposed to be. You never know.
There you go. Wow, that's pretty good. What do the directions say? I think it says we're,
Yes.
does it tell us what to round to? Can be solved in more than one way, blah, blah, blah. Let's just give everything to 2 decimal places. Can we do that? So what would that one be? Say that again, 3.24? If we rounded?
Yeah.
3.24 decades. Don't forget to always put your units on. But that is how we do dimensional analysis. And all we're actually doing, everywhere that we break the table right here, every one of these, we're just splitting fractions and multiplying in between them. Do we have another?
right above me. She's just chilling.
Are you, sorry, I can't get the line. Tell me if it goes back to the window. Okay. So, let's pick one from page 2 to let me help you with, because you're gonna have to do 5 on your own, and I wanna make sure. So pick one on this page.
Do number 8 maybe?
Which one?
I don't know.
11 it is. Okay, eggs are shipped from a poultry farm in trucks. Each carton of eggs holds 12 eggs. The cartons of eggs are then put in a crate that holds 20 cartons. The cartons are packed in trucks that carry 3,125 crates of eggs. How many trucks will it take to carry 3.75 times 10 to the 6th eggs? Okay. So, let's think. What is 3.75 times 10 to the 6th? Well, let's review just really quick our scientific notation. Since the exponent is positive, is that a really big number? Teeny tiny decimal?
A big one.
Big one, because it's positive. That's all the sign on the exponent tells us. Big, not tiny. So if it's big, I need to move my decimal to the right, so I get a big number. So there's 2, and I gotta go a total of 6 places. How many zeros would I need to put on the end of that? 4. So 375 with 4 zeros. Now, is that a little easier for you to work with? Okay, so we'll work with that. We've got 3,750,000 eggs that we need to ship. Right? And I've got to figure out how many truckloads that is. So first thing is they pack the eggs in a what? Carton. In a carton. And one carton holds 12 eggs. Then, what do the cartons go in?
Crate.
Then the cartons are put in a crate. So, one crate holds how many cartons? So we make that. Then, the crates get put where, Brenda? And the truck holds how many crates? 3,125. So, eggs cancels, cartons cancel. Crates cancel. What's the only unit we're left with? So now, once you are down to the only unit you need, what do? Multiply across the top, multiply across the bottom, then divide. That is one thing that every student, no matter whether they like math or not, when they get to a concept that they are successful at, they feel pride and they like that feeling. So the more opportunities we can give them to feel that, the more they'll like that. Is that how much it takes? Did we get 4 point something? Or did we get even? Awesome.
You do.
A pretty number. All right, and then the last page.
And then you find
Actually, you know what? Wait, let's go to the back. I want to show you something really quick, but it's not showing you on here. What happens if you've got to do like square or cubic? Suppose you have 81 square centimeters, and you want to know how many square millimeters that is. So it has a power on it. Make sense? All right, so the way that I teach this one with dimensional analysis, so you have 81, but you know centimeters squared is the same thing as centimeters times centimeters. Do you agree with that? Mm-hmm. So that means I need two fractions with a centimeter on bottom to get rid of both of those. And what am I trying to go to? Millimeters. So I'm taking both of those millimeters. With me? Which one's bigger, a centimeter or a millimeter? So that's our one. How many millimeters in a centimeter? 10. So what do we have left? We have 2 millimeters left. Well, what is 2 millimeters? Millimeters squared. So if we multiply across the top, 81 times 10 times 10, we get 8100. Across the bottom, you have 1 times 1 times 1, so it'd just be 1. So anytime you see a power, it just means you have to undo that fraction that many times. So if it had been like cubic feet and had 3 on it, you would have had to use the feet on the bottom 3 times to get rid of all 3 of them. That's the only difference. Make sense? Okay. How do we feel about that? Feel good. All right, I got 30 minutes left. Phew, we're right on time. All right, so last thing, this is actually a little early. You're not gonna get to area until after spring break, but I feel that you have worked with area and perimeter of triangles and rectangles and parallelograms your entire lives. So with a little refresher online, that's easily done. But regular polygons, not everybody has worked with those. And especially if you guys ended up being in geometry around COVID time. How's my video back there? Is it still going? I'm going to be super sad if that thing turned off. Thank you, Helen.
Yeah, it's going.
So this activity is actually from the same curriculum. It's from Carnegie Learning, but it is from the high school geometry text. I'm trying to get versions, okay? This one is just a video that shows why the formula for a triangle's area is base times height divided by 2. And it's for elementary students, so it's very straightforward, and it will make you a better teacher if you know why those formulas are the way they are. So much so that these, over spring break, these are just videos. Nothing more of me teaching these concepts in a flipped classroom high school setting. So like on this one, I explained to you when I was much, much younger, 30 something, why the formula for the area of a trapezoid is the way it is, okay? So you don't have to watch every single example problem in here if you don't want to, but at least watch the first 2, 3, 4 minutes of each one of these and see why that formula works the way it does, okay? So, today we're gonna be working with regular polygons. What are regular polygons? Here we go. Yeah. Polygons where all the angles and all the sides are equal, same length. Okay, good. So students don't know this yet, right? But we're gonna be talking in this lesson about congruent polygons and the apothem. In high school, did your teacher say it any other way than apothem? Did somebody do you? Never heard, never did apothems? Okay, so that's important. So this is new stuff, right? All right, so the specifications, the real life specifications, bless you, for the smallest possible yield sign are shown below. What do you notice about the yield sign? So all the angles are what? They're all the same. What are they all? 60. And what about side length? They're all the same, and they're all what? 30. They're all 30. So all sides are 30 inches, and all angles are 60 degrees. So we do try to model in this type of curriculum where students, this type of textbook actually becomes an interactive notebook for a student, and it becomes like their diary of what they learn. So we try to get them to write incomplete sentences, or at least complete thoughts. It might not be a good sentence, but so that they can go back later and understand what they were thinking. So let's look at the specifications for a do not enter sign. What do you notice about the quadrilateral for a do not enter sign? Okay, so all angles are 90. And
All sides are 30.
all sides are 30 inches, same size as the other one. What about a stop sign?
All angles are 135.
So what we are trying to do is to get our students to come up with a definition for what all on their own.
Are you asking a question?
So we have our kids write this over and over again because we're trying to get them to realize this right down here. A regular polygon is a polygon that has all the sides congruent and all the angles congruent. So this is a new concept. Here are some other two possible sizes for a yield sign. So we could have 36-inch sides, or we could have 48-inch sides, right? Are these signs regular? Are they regular polygons? How do you know? Okay, so they still have congruent sides and congruent angles, right? So yes. They polygons because they have congruent angles and congruent sides. So that's kind of what I was talking about. They may not be legitimate complete sentences. We might have shortcuts in them like because, or the symbol for congruent instead of the word congruent, or the symbol for angles instead of the word angle. So we might be shortening it down, but we still have complete thoughts. So when we go back, we understand the notes that we've taken. These become their notes. So let's look at the yield sign, bless you.
Thank you.
The yield sign from question 1 is shown here with an approximate height. How can we calculate the area of this yield sign? What do you guys know about the area of a triangle? What is the formula for the area of a triangle?
Did you say it was base times?
The way I teach it and the way I use it is base times height over 2. Some of you may do it 1/2 base times height. So same formula, right? I like to do base times height over 2. What is the base of this triangle? 30. What is the height? 26 all over 2. I think if I do my divide by 2 right there, will make the easiest multiplication problem when I'm done. So that becomes 3, 9, and 0. So, what are we measuring in? Inches. And area is always square units, okay? Linear measure, perimeter. I don't know if I'm on the screen. I should write it up there, so I am on the screen. Over here. Perimeter or circumference, either one, is always linear. That means to the first power. Feet to the first power. Centimeters to the first power. Area, because you multiply length times width, you multiply centimeters times centimeters, you have square units. So square centimeters, square feet, right? Length times width. When we get to capacity, after spring break, when we get to volume, then we have length times width times height. So inches times inches times inches gives us cubic units. So if you're finding volume, the units are always cubed. You just got to figure out which unit it is, right? If you're finding area, the units are always squared because you're multiplying 2 units together. With you? Okay. Important to teach your kiddos. What if, let's calculate the area for the do not enter sign in question 2. What shape is the do not enter sign? It's a square. And the formula for the area of a square is just side length squared because all the sides are the same, right? What was that one, 12? 30 again? 30. So this time it's 30 squared, which is the same thing as 30 times 30, which would be 900. It was inches, right? Yes. Okay. It's really important. I know that your math teachers may not have always done this, but for students to actually progress and to keep progressing in math and keep progressing in math without getting to a point where they kind of reach a top that they can't go past, it's important to teach them that math is a language just like English is a language. And so when they're doing problems like this, if they just give you an answer, like 900, even though they did a lot of that work in their head, that would be like turning in a paragraph to your English teacher and only putting the concluding sentence down. What would happen if you went to Comp 1 and you were supposed to write a paragraph about the community here on campus, right? Student community on campus, you're supposed to write one paragraph, and you go to Comp 1 and you turn in just your concluding sentence. Is that gonna go well? Exactly. Don't let them get away with that in your class either, because this, right, that's their opening statement. That tells you what formula they're using. If they get their opening statement off, you know everything after it's off. But if all they give you is a number, and that number happens to be 725, as the teacher, how are you gonna assess where they went wrong? Right? You can't help fix their misunderstanding if you don't know where the misunderstanding took place. So that's why it's so important for you to convey to them, you read their work just like you read their paragraph in English class, right? It's their thoughts, and it's important in math, just like English. You guys are blazing over on me. I feel like I'm preaching math up here, and you guys are going to sleep Sunday morning. All right, let's do one more, then I'll let you go. I gotta get to the apophthegms. All right, so when we start doing things like regular polygons, instead of trying to learn a new formula for every polygon, one for hexagon and one for heptagon and one for octagon, there are formulas for all of them. Instead of doing that, let's learn a technique that works for all the regular ones. We can take any regular polygon and cut it into congruent triangles. So the stop sign, since it has 8 sides, it's gonna have how many congruent triangles? 8 congruent triangles. If I know that a side of that stop sign is 12.4 inches, that gives me the base of one of those triangles. Then I know that the apothem, which is the perpendicular distance from the center to the middle of that base, that gives me the apothem, which is what? 15, right? Can I find the area of this triangle? Yes. So the area is base times height over 2. So 12.4 times 15 over 2. What's that? 2 times 15. Oh, I don't really want to do that in my head.
93.
Thank you. So each of these triangles is 93 square inches. So the question is, how many of those triangles do you have? 8. So 93 times 8, because you have 8 triangles, right? So 720 and 24 is what? 744? Does that make sense? Uh-oh. Okay. So down here, if I asked you, if I put this on the test and I tell you to draw an apothem, how do you draw an apothem onto one of those regular polygons? What's the rule for an apothem?
You just pick one side.
Pick one side, any side, and where does it go?
To the middle.
Has to go to the middle of that side, perpendicular, right? So this one, we can make it go over here if we wanted. But it has to go to the middle. The most common mistake are for students to draw it to a corner, to a vertex. That's a slant height. That's a different height, and we need it for something later on, but we don't need it now. It's the distance, the height distance of that triangle, right? Okay. So, look at this one. This one's not an octagon anymore, it's only a hexagon. Could you find the area of that hexagon? What would you do?
Find the area of those.
Find the area of one of those congruent triangles and just multiply it by 6, because you got 6 of them. That works with every regular polygon. Okay, with that, the key there is knowing the apothem. Okay, they'll try to trick you by giving you the apothem, but then they'll also tell you the height of one of these slant heights over here and try to distract you with a different number. So watch out, you need the apothem, okay? All right. Is that good enough to get you guys through spring break? You have nothing due for me after this weekend until we come back from spring break, right? Nothing due over spring break. I don't think these, does it say you have to submit it? Let's look. Dimensional analysis. No, let's see. I'm trying to be very good about putting this on here. Addie asked me to. In the directions of everything, it should clearly state what you're supposed to do with it. So the one you just asked about, Brenda, it says, place your completed artifact in your portfolio. It does not say to upload it. It will say in the
And you
directions what
multiply by
you do with
six,
everything.
you have that number, and then
Okay.
you multiply by six, you get 41.
Angie, will you turn off my?
And then, yeah, and you get.
Yes, I
41.
need my self-assessment back so I can give you points for today. Assess your